Welcome to the Deep Dive. Before we really get going today, I want to encourage you to head over to https://learnxyz-in for a bunch more great articles like the one we'll be looking at today.
It's really a great resource for anyone who loves to learn.
Absolutely. So today, we're diving into the world of fast radio bursts.
Or FRBs for short.
Right, FRBs. So these are these super intense bursts of radio waves that...
They only last for milliseconds.
Milliseconds, wow. And they've been like a huge puzzle for scientists since they were first discovered back in 2007.
It's like someone out there is sending these incredibly short and bright radio signals to us.
And the article we're looking at today says these signals come from galaxies that are billions of light years away.
Billions. That means whatever is causing these bursts has to be unimaginably powerful.
Yeah, the article mentions that an FRB releases as much energy in a millisecond as the sun does over several days.
It's kind of hard to wrap your head around that much energy packed into such a short amount of time.
For sure. So how do we even find out about these FRBs? It seems like they'd be pretty easy to miss if they happen so fast.
You're right about that. The first FRB, now known as the Lorimer burst, was actually discovered by accident.
Really?
Yeah, Duncan Lorimer and his student David Narkevich were going through some old data from the Parkes Radio Telescope in Australia.
Weren't they looking for pulsars?
Exactly. Pulsars, those spinning neutron stars that emit beams of radiation. They were sifting through all this old data and boom, they found this weird signal.
So they were looking for one thing and ended up finding something totally different.
It was like finding a hidden treasure. The signal was so strong and so short that at first they weren't even sure what it was.
So one minute they're hunting for pulsars, the next they've stumbled onto this whole new cosmic phenomenon.
Pretty much.
That's amazing. But how do they know that this signal, this FRB, was coming from outside of our galaxy?
That's where something called the dispersion measure comes in. It's a little bit technical, but it boils down to how radio waves travel through space. You see, as these waves travel, they get scattered by all the gas and particles floating between galaxies.
So the farther a wave travels, the more scattered it gets.
Exactly. And that's how we know that these FRBs are coming from these incredibly distant galaxies. Some are billions of light years away.
It's like looking through a foggy window.
Yeah.
The thicker the fog, the blurrier the image. So by measuring how blurry the FRB signal is, scientists can figure out how far it's traveled.
That's a great way to put it.
It's mind-boggling to think about. It's like these FRBs are messages from across the universe. But what could be creating such powerful and short signals?
Well, that's the million-dollar question, isn't it? There are a lot of interesting theories out there, but one of the top contenders is a type of neutron star called a magnetar.
Magnetars. I remember learning about those in school. They're neutron stars, but with incredibly strong magnetic fields.
Right. Imagine a star many times bigger than our sun squeezed down into a ball just a few miles across. The gravity there is so strong that it crushes atoms and forces electrons to merge with protons. You end up with an object made almost entirely of neutrons.
Dense doesn't even begin to describe it.
And then take that incredible density and add the strongest magnetic fields in the universe, trillions of times stronger than Earth's magnetic field. And that's a magnetar.
So it's like a neutron star on steroids.
Pretty much. And with that kind of power, it's not hard to imagine how they could be behind FRBs.
Okay, I'm starting to see why magnetars are a suspect. But how exactly could they create these intense radio bursts?
The leading idea is that the magnetic fields of magnetars can become unstable. Think of it like the crust of a neutron star cracking and shifting, releasing massive amounts of energy.
So it's like these magnetars are just waiting to unleash these bursts of energy.
It's possible, and there's actually some evidence to support this theory.
Oh.
One of the most important discoveries in FRB research came in 2020 when scientists found an FRB right here in our own Milky Way galaxy.
When an FRB in our own galaxy?
Yeah, it was a huge breakthrough. And guess what? The source of this Milky Way FRB was a known magnetar called SGR 1935 plus 2154.
That's incredible. So it's like they caught the culprit red-handed.
It was the strongest evidence yet that at least some FRBs come from magnetars.
So case closed. Magnetars are the source of all FRBs.
Well, not so fast. Remember, these bursts come in a lot of different flavors. Some are one-offs, some repeat. Some even have patterns, while others seem totally random.
So maybe there's more than one way to make an FRB.
Exactly. And that's what makes this field so exciting. It's like a giant cosmic puzzle with new pieces being discovered all the time. Another possibility that scientists are looking into is the collision of super dense objects like neutron stars or even black holes.
Now, those are some seriously extreme events. What makes scientists think they could be connected to FRBs?
When these kinds of objects collide, they release mind-blowing amounts of energy, mostly in the form of gravitational waves.
Right, those waves that were first detected back in 2015, proving Einstein's theory of general relativity.
That's the one. Those detections were huge, and they opened up a whole new way of looking at the universe. And some scientists think that certain types of FRBs might be linked to these gravitational wave events.
So you're saying that we might be seeing both gravitational waves and FRBs from the same event.
That's the idea. But there are some challenges to this theory, too.
Like what?
Well, if these collisions are so powerful and destructive, wouldn't they just happen once? How would that explain the repeating FRBs?
That's a good point.
It's possible that some of the repeating FRBs come from something else entirely, like maybe a neutron star interacting with a companion star or a cloud of gas. But there's still a lot of debate in the scientific community.
It sounds like we've got a real cosmic mystery on our hands. We've got these intense, millisecond-long bursts of radio waves coming from faraway galaxies, and they could be caused by supermagnetic neutron stars, or maybe from these incredibly powerful collisions of super-dense objects.
It's enough to make your head spin.
It definitely is.
Yep.
But before we go any further, I think it's worth taking a moment to really appreciate why these discoveries are so important.
Absolutely. These FRBs aren't just some cool space stuff. They're giving us a whole new way of looking at the universe.
So it's not just about figuring out what causes them. It's about what they can teach us about the universe as a whole.
Exactly. FRBs are like messengers from the distant cosmos. They carry information about everything they've traveled through. Remember the dispersion measure we talked about?
Yeah.
Well, it doesn't just tell us how far away something is. It can also tell us about how matter is spread out in the universe, including that mysterious stuff called dark matter.
Okay, now you've got my attention. Tell me more about how FRBs can help us understand dark matter.
Well, dark matter is this weird stuff that makes up a lot of the universe's mass. But we can't see it directly. It doesn't interact with light. But we know it's there because of its gravity. It affects how galaxies move and how light bends.
So it's like the invisible glue holding the universe together.
That's a good way to think about it. And here's where FRBs come in. As these bursts travel through space, they pass through both regular matter and dark matter. And the more matter they encounter, the more their signal gets dispersed.
So by looking at how much an FRB signal has been spread out, scientists can actually map out where the dark matter is.
Precisely. It's like using these FRBs as cosmic X-rays to peer into the hidden structure of the universe.
That's incredible. We're using these tiny little bursts of radio waves to create a map of the invisible universe. But wait, there's more, right? The article also mentions that FRBs can help us test some of the most fundamental laws of physics.
You're right, because these bursts travel such huge distances. They give us this unique opportunity to put Einstein's theory of general relativity to the test in extreme environments.
Einstein's theory of general relativity, the one that says gravity is the warping of space and time. How can FRBs help us test that?
Well, according to general relativity, massive objects like galaxies can actually warp space-time, causing light to bend around them. This bending of light is called gravitational lensing, and it can affect the path of FRB signals as they travel towards us.
So by studying how FRB signals are distorted by this lensing effect, scientists can check if Einstein's theory holds up in places with really strong gravity.
Exactly. It's like using these bursts as cosmic probes to explore the fundamental fabric of the universe. And so far, the observations of FRBs match up with Einstein's theory, which just makes it even more impressive.
This is all so mind-blowing. We've gone from these seemingly random bursts of radio waves to mapping dark matter and testing one of the cornerstones of modern physics. But before we get carried away, I think it's time to take a closer look at some of the specific discoveries and challenges in FRB research.
You're right, there's still so much more to uncover. We need to talk about the different types of FRBs and the amazing telescopes that are helping us find them.
Well, and let's dive back in. But first, a quick reminder to everyone listening to check out https://LearnXYZ-In. That's where you'll find the article we've been discussing today, along with a ton of other amazing scientific content.
It's definitely worth a visit.
Okay, we'll be back in a flash to keep exploring the incredible world of fast radio bursts. Welcome back to the deep dive. We're continuing our journey through the fascinating world of fast radio bursts, and I have to say, I'm even more hooked now than when we started. These bursts are like these little cosmic beacons, giving us clues about the universe's structure, the stuff it's made of, and even those mind-bending laws of physics.
I'm glad you're enjoying it. And as we dig deeper into the specifics of FRB research, you'll see just how complex and fast-moving this field really is.
I'm ready for more. You mentioned earlier that there are different types of FRBs. Can you tell me more about that? What makes some stand out from the others?
One of the things that make FRBs so interesting is their variety. Some of them are just like a one-time flash in the pan. They burst once, and then we never hear from them again. But then we've got the repeating FRBs. These guys send out multiple bursts over time, and they're really intriguing.
Yeah, those repeating ones really make you wonder. It's like someone out there is trying to send us a message.
It's a tempting thought, isn't it? But even though the idea of alien signals is really cool, scientists are focusing on natural explanations for those repeating bursts.
Okay, I can understand that.
Yeah.
So what are some of the top ideas for why some FRBs repeat and others don't?
Well, it's kind of like a puzzle that we're still putting together. One possibility is that different kinds of objects or events are causing these different types of FRBs. Remember those magnetars we talked about?
The supermagnetic neutron stars.
Yeah. Some scientists think that those repeating FRBs could be coming from magnetars that go through these multiple starquakes or magnetic reconnection events.
So you're saying it's like these magnetars are having these magnetic tantrums, and each time they do, they send out a burst of energy.
It's a colorful way to put it, but that's the general idea, and it seems to fit with what we're seeing with some of these repeating FRBs. Some of them show changes in how bright they are and even how often they burst.
That makes sense. What about the ones that only burst once? Could those be caused by something else?
Definitely. Remember those crazy collisions of neutron stars or black holes?
Hard to forget those.
Those are incredibly powerful events, but they only happen once.
So maybe some of these FRBs are like the last screams of these objects as they crash together and become one.
It's a dramatic picture, but it could be true. And the fact that we've seen both gravitational waves and regular light from these collisions makes the idea that they could also produce FRBs pretty believable.
It's amazing how all of these discoveries in astrophysics are connected like that. But I'm curious about actually catching these bursts, especially those one-time ones. How do scientists even manage to see them happen?
That's where the technology comes in. Remember how that first FRB was discovered by chance while looking through old data?
Yeah.
These days, scientists are using telescopes that are specifically designed to hunt for FRBs.
So it's not as simple as pointing any old telescope at the sky and hoping for the best. What makes these FRB hunting telescopes so special?
One of the big things is their wide field of view. Because FRBs are so unpredictable, you need a telescope that can scan huge chunks of the sky at the same time. That way you have a better chance of catching one of these quick bursts.
It's like casting a really wide net to catch these cosmic fireflies.
Exactly. And they also have to be incredibly sensitive. These telescopes need to be able to pick up the faintest signals coming from billions of light years away.
So we're talking about some serious cutting-edge tech here.
You bet. One of the most successful FRB hunters out there is the Canadian Hydrogen Intensity Mapping Experiment, or SHUMSLATE for short. It's been operating since 2018, and it's found a ton of FRBs.
Chump. That's the one that looks like a giant half-pipe, right?
You got it. It's got this unique design that lets it see a huge part of the sky, and it's got some super advanced processing power so it can handle all that data and pick out the FRB signals.
So it's like this huge cosmic vacuum cleaner sucking up FRBs from all over the sky.
I like that analogy. And it's been doing an amazing job. Since it started working, CHME has found hundreds of FRBs, including a lot of repeating ones.
Hundreds. That's a crazy amount of data. What have we learned from all those observations?
Well, one of the biggest things is that FRBs are way more common than we used to think. Back before CHIME, we only knew of a handful. But now we know they're happening all the time, all over the place.
So it's like we were only looking at a tiny piece of the picture before, and now CHIME has opened up this whole new view.
That's a great way to put it. And this huge number of FRBs isn't just exciting for scientists. It also means we can start using them as tools to study the universe in new ways.
Like mapping out dark matter and testing those physics theories we talked about earlier.
Exactly. The more FRBs we find, the more detailed and accurate our maps of the universe become. And the better we can test our understanding of how physics works at the most fundamental level.
It's like each new FRB is a clue that helps us solve this giant cosmic puzzle. But I imagine there are still some challenges in using FRBs for these kinds of things.
There are definitely challenges. One of the biggest ones is figuring out exactly where these FRBs are coming from. Remember, they're super short, and they often come from these faint, faraway galaxies.
So it's like trying to find a tiny speck of dust in a giant warehouse. But the warehouse is billions of light years away.
It's tough, but scientists are coming up with clever ways to get better at pinpointing these FRB sources. One way is to use multiple telescopes at the same time to observe the same FRB.
So it's like using triangulation to figure out where the signal is coming from.
Precisely. And as our telescopes get better and more powerful, we'll be able to locate these FRB sources with even more accuracy, which will let us study them in much greater detail.
This is all so fascinating, but I feel like we've only scratched the surface of this whole FRB thing. Before we wrap up, what are some of the big questions that scientists are still trying to answer?
Well, one of the biggest mysteries is still nailing down exactly what's causing all these different types of FRBs. We have some good ideas, like those magnetars and the collisions, but are those the only explanations? And how do we explain all the different weird things we see with FRBs, like how often they burst and how much energy they release?
It's like every time we find an answer, we end up with 10 more questions.
And that's what makes science so exciting. It's about pushing the boundaries of what we know and being okay with not having all the answers right away.
I love that. And I can't wait to see what new discoveries come out of FRB research in the years to come. Welcome back to the Deep Dive. It's been quite a ride exploring the world of fast radio bursts. We've gone from those first confusing signals to this whole new frontier of space science. It's amazing how FRBs are changing how we think about the universe, its structure, and even the laws of physics themselves.
It's definitely a field that's full of excitement and new discoveries. It seems like every time we learn something new about FRBs, it opens up even more questions about the universe.
Speaking of new discoveries, you mentioned before the break that the future of FRB research is looking pretty bright. What are some of the things that scientists are most excited about?
Well, one of the biggest things is that we're going to be getting a lot more data in the coming years. There are new telescopes being built and planned that are going to be able to detect FRBs at an incredible rate. We're talking thousands or even tens of thousands of FRBs per year compared to just a handful a decade ago.
Wow, that's a lot of data. But I guess that's a good thing, right? More data means more chances to find patterns, to test our theories, and maybe even discover completely new types of FRBs that we haven't even imagined yet.
Exactly. With all this new data, we'll be able to make much more detailed maps of the universe. We'll be able to study how galaxies change over time, and we'll be able to test the laws of physics in ways that we never could before.
It's like we're getting a much clearer view of the cosmos.
Mm-hmm.
So with all this data coming in, how are scientists going to keep up? Analyzing thousands of FRBs sounds like a pretty big job.
It is a challenge, but that's where things like machine learning and artificial intelligence are going to be really helpful.
AI seems to be popping up everywhere these days. How is it being used in FRB research specifically?
Think about it this way. Each FRB has its own unique set of characteristics, kind of like a fingerprint. There's its duration, its frequency, how bright it is, and so on. By training AI algorithms on the data we already have, we can teach computers to automatically spot these fingerprints in the data from telescopes.
So the computers can sort through all the data and pick out the FRBs much faster than humans could.
That's right. That means human scientists can focus on the most interesting FRBs and really dig deep into what they can teach us about the universe.
It's like we're building a team of super smart robots to help us understand the cosmos. It's a pretty cool combination of human brainpower and technology.
I agree. But aside from just having more data, what are some of the specific goals that FRB researchers are working towards? One big focus is on building even better telescopes, specifically for finding FRBs. Remember Cheat Chime, the one that looks like a half pipe? That's been a fantastic tool, but the telescopes of the future are going to be even more powerful. They'll be more sensitive, they'll be able to see more of the sky at once, and they'll be able to tell us exactly where FRBs are coming from with even more accuracy.
So it's like we're upgrading to a whole new level of FRB hunting.
Absolutely. One project that's really exciting is the Square Kilometer Array, or SKA. It's going to be the biggest radio telescope ever built, and it's going to be spread across 2 continents, Australia and South Africa.
2 continents, that's massive.
It is. With all that power, the SKA is expected to detect thousands of FRBs every single day. It's going to completely transform our understanding of these phenomena.
The SKA sounds like it's going to be a game changer for all of astronomy, not just FRBs. I can't wait to see what they discover. But what about other advancements besides new telescopes? What else is driving the future of FRB research?
Another really exciting area is what we call multi-messenger astronomy. That's where we combine observations from different kinds of telescopes, not just radio telescopes, to get a more complete picture of what's happening in space.
You talked about this before, looking at FRB sources using different kinds of light like X-rays and gamma rays. Why is this multi-messenger approach so important?
Imagine trying to understand a whole orchestra by only listening to one instrument. You might get some of the melody, but you'd miss all the richness and complexity of the whole piece. It's the same with FRBs. When we look at them using different kinds of telescopes, we get a much richer and more complete understanding of what's going on.
So instead of just listening to the radio waves from FRBs, we're also looking for other kinds of light that might be coming from the same source. What kind of information can we get from doing that?
By combining observations from different telescopes, we can really study the environments around FRBs in detail. We can measure the temperature, the density, what the gas and dust near the FRB are made of. We can look for signs of stars being born or dying. And we can even search for clues about what kind of object or event created the FRB in the first place.
It's like having a whole team of cosmic detectives using different tools to investigate the scene of the FRB.
I like that. And the more pieces of the puzzle we find, the closer we get to understanding FRBs and how we can use them to learn about the universe.
This has been an incredible journey. We've gone from these strange bursts of radio waves to a whole new era of space exploration. It's mind-blowing to think about all the questions that FRBs are helping us answer and all the new questions they're making us ask. It really makes you appreciate the power of human curiosity and our desire to understand the universe.
I completely agree. And as we continue to explore the cosmos with better and better tools, I have no doubt that FRBs will continue to surprise and amaze us, revealing even more about the nature of reality itself.
Well said. And for our listeners who want to learn more about this fascinating topic, be sure to check out https://learnxyz.in. That's where you'll find the article that inspired this whole deep dive, along with a ton of other great scientific content. And while you're there, don't forget to like this episode, subscribe to our channel, and tell a friend who might also be fascinated by the mysteries of the universe. Thanks for joining us on this deep dive into the world of fast radio bursts.
Thank you.